Hey guys, this is Nikhil, and for those of you who don't know me, my name is Nikhil Kundu. I took AP Calc BC during the 2018-2019 school year, and today I will explain the concept of approximating function values. And you're probably asking yourself, how does this concept of approximating function values, this very broad concept, relate to what we're studying right now in Chapter 10, Infinite Series, which is the infinite summation of sequences. And hopefully by the end of this video, you will have gained a complete understanding of how this concept relates to the grand scheme of things in this chapter, Infinite Series, right? So this chapter, right, chapter 10, isn't going to be the first time that you're approximating values of functions using calculus, right? If you remember, in chapter 5, we studied a concept called linearization. And the basic premise behind linearization, right, was say you had a function that looked kind of like this, and you wanted to approximate the value of the function, say at this point over here, right? I'm gonna make this a different color so you can see it properly. Say this point over here, and I labeled this point x. But say x was kind of like an obscure number, like 2.01 or something like that, right? And it would be easier to find the value of the function at a point like 2, right? And I would name that point a, and say a is 2. So I would draw the line that's tangent to the function at 2, and I would use that line, right, to approximate the value of 2.01, and I'm going to pretend that's a tangent line, right? The function and the linearization are tangent, right? And the formula for this linearization concept is f of a plus f prime of a times x minus a, where a is the point of linearization, right? A would, so in this case over here, a would be 2, right? So you're doing the linearization at 2 to approximate another value like 2.01, right? Okay, so let's quickly do an example that deals with linearization so we can kind of segue into the bigger picture of how linearization relates to chapter 10, right? So say I had the function x cubed minus 2x plus 3, and I wanted to find the linearization of this function at the point a is equal to 2, right? So using this formula, I would need to find the value of the function at a is equal to 2 first, right? So I'd do 2 cubed minus 2 times 2 plus 3, which would get me 7, right? 8 minus 4 plus 3. And then I would need to find the value of the derivative, right? F prime of a. So I need to find the value of the derivative at a is equal to 2. And the derivative of this function would be 3x squared minus 2. Right, so the value of the derivative would be 3 times 2 squared minus 2. And that would get me 10. All right, so I have these 2 points. And now I can write my linearization equation, which would be, well, I'm going to name the linearization L of x, L for linearization, obviously, right? So that would be L of x is equal to my function value, right, f of a, and in this case, it would be f of 2, right, so that would be 7, plus f prime of a, so my function, the derivative of my function at a, which would be 10, times x minus a, times x minus a, and a would be 2. Right, so this right here is my equation for the linearization. So let's see how the linearization, the approximation that I get from this linearization for a point, let's say the point is 2.01, right? So let's see how close the approximation I get from this linearization is to the actual function value at 2.01. So my function is x cubed minus 2x plus 3, and let's see the actual value of the function, right? So it would be 2.01 So I'm going to say approximations. Right, so my actual function f of 2.01 is equal to 2.01 cubed minus 2 times 2.01, I think it was plus 3, right? And this would get me a value of 7.100601. So that would be the actual value of my function at point 2.01. All right. So now let's see the value of the linearization, right? So my linearization, let's see how close it is. So, 2.01 is equal to, well, it would be 7 plus 10 times 2.01 minus 2, and that would get me 7.1. So 7.1 is my linearization. 7.100601 is my actual function value. So they're pretty close, right? The linearization is 0.00601 away from the actual function value, and that's pretty close, right? But what if we wanted to get closer? What if we wanted to minimize this error? And how would we minimize the error? Well, let's look at this graph over here. So obviously this curve that I drew isn't an actual depiction of the function that we have, the function that we're creating a linearization for, but it could suffice, right? So we have this linear equation that's tangent to the graph, and we're using that to approximate. But what if instead of a line we use a polynomial, right? What if we use a quadratic, like that, right? That would be a pretty good approximation, right? If we had the perfect quadratic, or if we maybe used a cubic function, right? Like that would also be a pretty good approximation. So you know what? Why don't we graph the linearization, and why don't I graph some polynomials on Desmos, and maybe you could see how the three equations compare. All right, so I have Desmos open here, and I have the actual function that we have, right? And I have a linearization plotted. So if we go over to 2, right, that's over here, the function and the linearization, they have the same value, right? They're overlapping at this function because the linearization is tangent to the graph of the function at 2, right? But now if we go over to 2.01, right, that's like over here. Zoom in like all the way. This is about 2.01. So you can see that the graph of the actual function, the graph of the linearization kind of have a gap in between them, right? So remember how I said that, if we had a quadratic, right, if we increase the power, right, if we didn't have a line, but we had a curved function, a curved polynomial, let's start off with a quadratic, the approximation might become better, right? So let's say we had this quadratic over here, and you don't need to worry about how I got this quadratic just yet. We'll get to that later. But you can see that the approximation already got a lot better, right? The linearization is over here in the quadratic, and the quadratic and the actual function are like so close to each other, right? The error is a lot less, presumably, over at 2.01. But there's still like a gap in between them, right? So what if we increase the power to have a polynomial to the third power, right? A cubic function. And that's what this thing is over here, this last function that I have. And once again, you don't need to worry about how I got it just yet, but you can see that they're overlapping now. They're essentially overlapping. And if I zoom out, you can see that wow, it's a lot. You can see that the last function that I had, and the actual function that we were using from before, they're actually the same exact thing, right? They're overlapping the entire way. And let's kind of look into this let's look into this idea, how if you increase the powers, right? If you add more and more terms to increasing powers, right? How you get better approximations of function values. Alright, so we're back here, and I have all of the functions that I graphed previously on Desmos. I wrote them down over here. So we have the linearization, right, and then we have the quadratic, and then we have the cubic function. So as we saw before, right, as I added terms of greater powers, right, as I kept adding stuff, as I added more and more stuff, I got better approximations. My error decreased, and we saw that in the graph. But I will actually, let me write down the actual values that I get when I plug in something like 2.01 into each of these functions. So L of x, as we calculated before, the regular linearization, my error was 7.1. And now if I plugged in 2.0, so this would be L of 2.01. Hold up. Right, so if I plugged in 2.01 into a, which is my a of x, which is my quadratic, I would get 7.1006, and I'll remind you that our actual function value is 7.100601, so we're getting way closer. And then as we saw in Desmos, when I had b, which was my cubic polynomial, the two graphs overlapped, and I had an exact value, and an exact approximation, which makes sense because b is a cubic approximation, and my original function was also cubic, right? So that turned out to be 7.100601 on the dot. So yeah, I think we've established that as we add powers, right? As we add powers and go on further and further, we get a closer and closer approximation. So I mean, I can't say, in this case, we can't say that as we go towards infinity, we get a better approximation because, as it turned out, when I got to the third power, my approximation was exact. But in other cases that you're going to explore later on in this chapter, later on in this section, you'll see that you can keep adding on powers, right? You can go to the fourth, you can go to the fifth power, sixth power, and you can keep adding stuff on, and the approximation will just become better, but it won't become exact. It might not necessarily become exact. So the question still stands, how did we get these functions, right? And in order to get these functions, we need to design a custom polynomial. So let's take a step back. So we've established that use these polynomials to approximate other polynomials, to get values of other polynomials like this one that we've dealt with before. Or it could be something as general as something like sine of x, right? So we could have polynomial approximations of values on the sine of x graph, right? So say I had something like that. Let's pretend that that's a sine of x graph, and I wanted to approximate this value over here. Well, I could have a quadratic. That approximates that value, right? So say I had a function p of x, and I wanted to approximate p of x with a polynomial, and all I was given regarding p of x were these derivative values, right? These derivative values over here, and I wanted to find a polynomial that approximates p of x at x is equal to 0. So if you're up for a challenge, I urge you to pause the video and see if you can do this. See if you can find this right polynomial p of x, and get these a sub 1, a sub 2, all these subscript values. If you can find these values just by looking at these derivatives. So assuming you paused the video and tried it, let's see how we can do it. So to find the first value, a sub 0, it won't be that bad, considering all we need to do is plug in 0 wherever there's an x, and we'll basically get a sub 0, which is 5. But I'll demonstrate it. So, well, p sub 0 is 5. So, I'm just gonna write p sub 0 is equal to a sub 0 plus a sub 1 times x But now, since we're doing this at x is equal to 0, we're just going to substitute 0 in for x. Plus a sub 2 times x squared, 0 squared, plus a sub 3 times 0 cubed, plus a sub 4 times 0 to the 4th. Right? So we have this, and then obviously anything times 0 is just going to be 0. So that becomes 0 too, this becomes 0, this becomes 0. And we're just left with p of 0 is equal to a sub 0. And we were given that p of 0 is equal to 5 right here. So 5 is equal to a sub 0, very simply. Alright, so how do we find a sub 1, and a sub 2, and a sub 3, and a sub 4, right? Well, maybe we could use the value of the first derivative. And since they gave us a value of the first derivative, why don't we find the derivative of p of x, right? Well, since this is a polynomial, right, we can use the power rule very easily. So let's find the derivative of p of x, right? So p prime of x is going to be what? It's going to be, well, we're just going to derive term by term. So the derivative of a sub 0 is just a constant, right? So that's just going to be 0. Plus a sub 1 times x, right? A sub 1, that's just going to be a sub 1. Plus a sub 2 times x squared. So now using the power rule, and a sub 2 is a constant as well, so it's going to be 2 times a sub 2. We're going to bring the 2 down as the power, so 2 times a sub 2 times x. Right? That's going to be the derivative of that. And then the next term is going to be 3 times a sub 3 times x cubed. And then we have 4 times a sub 4 times x. That's x cubed. Oh, did I say x cubed over here? I meant x squared. So now if we want to do p prime of 0, right, we just plug in 0 wherever there's an x, right? So it's going to be 0 plus a sub 1 plus 2 times a sub 2 times x. So that's just going to be 0 plus 3 times a sub 3 times x squared. So 0 in there is just going to make everything a 0. And then everything over here is going to be a 0 as well. So then p prime of x is just going to be equal to a sub 1. Well, p prime of 0 is going to be equal to a sub 1. And we were given that p prime of 0 is equal to 7. So it means 7 is going to be equal to a sub 1. Alright, so we have the a sub 0 value and we have the a sub 1 value. Now what is a sub 2 going to be? Right? So in order to find a sub 2, well, let's do the same thing as we did. Let's do the same thing we did with the first derivative, except now we're gonna use the second derivative of the function. Right? So now it's gonna be 0 plus 0 plus, now we're gonna take, so I'm going to take the derivative of p prime now, right? So the first term is 0, so the derivative is going to be 0. So a sub 1, since that's a constant, when I take the derivative of that, that's going to be 0. Plus 2, then I'm just going to be left with 2 times a sub 2, right? So if I take the derivative of this, that's going to be 2 times a sub 2. And then after that, I need to take the derivative of this over here. So I'm going to be left with 3 times 2 times a sub 3 times x. Right. Now finally, if I take the derivative of the last term, I get 4 times 3 times a sub 4 times x squared. Alright, so now if I plug in 0 everywhere I see an x, right, I can plug in a 0 into there, I can plug in a 0 into here, these terms cancel out. So they gave me the fact that p double prime of 0 is equal to 11, so I can set 11 over here. So 11 is going to be equal to 2a sub 2, which means a sub 2 is going to be equal to 11 divided by 2. All right. So we have a sub 0, we have a sub 1, we have a sub 2. So now I guess we could do the same. So in order to find a sub 3, we could do the same thing we did for p prime of 0 and p double prime of 0, right? We can use the third derivative that they gave us, which is 13. So p triple prime of 0, third derivative. So the first two, actually the first three, so I'm taking the derivative term by term of this, right? So this is also a constant, so this is going to become a 0. Then over here I'm going to be, so this is times x, by the way. So this is going to be right over here, this derivative, the derivative of this term over here is going to be 3 times 2 times a sub 3, right? The x just gets left out, and the a sub 3 is a constant. And then over here, the derivative of this is going to be 4 times 3 times 2, the exponent comes down, times 2 times a sub 4 times x, right? And when I substitute 0 in wherever I see an x, this term cancels out because I plug in a 0. I plug in a 0 over here. So this term cancels out. And then I'm just left with p triple prime of 0, and they gave me that p triple prime of 0 is equal to 13. So 13 is going to be equal to 3 times 2 times a sub 3. And in order to find a sub 3, I just divide 13 by 3 times 2. Alright, so I have a sub 0, a sub 1, a sub 2, a sub 3, and finally, I'm going to do the fourth derivative. The fourth derivative of the function is, well, so all these terms are just going to be 0, so I'm just going to be left deriving that term, so that's going to be 4 times 3 times 2 times a sub 4. That's going to be the derivative of this term over here. And they gave me that p to the fourth derivative of p at 0 is equal to 17. So 17 is equal to 4 times 3 times 2 times a sub 4. So in order to find the value of the value of a sub 4, I just divide 17 by 4 times 3. 4 times 3 times 2 is equal to a sub 4. So I have my a sub 0, a sub 1, a sub 2, a sub 3, and a sub 4 values. So I can construct this polynomial now, right? So I have the derivative values written here. So let's start plugging them into this polynomial form over here, right? So we're going to start off with a sub 0, and we found a sub 0 to be 5. And we'll add that to a sub 1 times x, and a sub 1 is 7. So it'd be 7 times x, and we're adding this to a sub 2 times x squared. So that's going to be 11x squared over 2. Plus a sub 3 times x cubed. So that's going to be 13x cubed over 3 times 2. And then finally we have a sub 4 times x to the 4th, so 17x to the 4th over 4 times 3 times 2. Alright, and just an FYI, 3 times 2, right, when I say 3 times 2, that can also be rewritten as 3 factorial. In the same way, 4 times 3 times 2, technically times 1, is rewritten as 4 factorial. So something like 7 factorial would be 7 times 6 times 5 times 4, so on, to times 1, right? Something to keep in mind is that 0 factorial is not equal to 0. 0 factorial is actually equal to 1. So just keep that in mind. So with all of that being said, well, first off, whoever, if you estimated this, if you tried to figure this polynomial out by yourself earlier on, hopefully this is what you got. But yeah, so with all that being said, this polynomial can be rewritten, these terms can be rewritten as 13 times x cubed over 3 factorial, right? Plus 17 times x to the 4th over 4 factorial, right? So I can use these factorials. And then this one would be 11x squared over 2 factorial. This would be 7x technically over 1 factorial. And this would be, well, 5. And we can say that's 0 factorial over here. So, because 0 factorial is equal to 1. Right, so maybe we can see a pattern kind of forming here. Right, so let's say we took the second term of this polynomial sequence, right? So this would be the 0th term, this would be the first term, this is the second, third, it's the fourth term. So yeah, so if we look at the second term, right, we can see that the second term is being, well, x is being raised to the second power, and everything's over the second, well, 2 factorial, right? And okay, so we have it being raised to the second power, and we have 2 factorial on the bottom. But what's this 11 doing here, right? Well, if we look back in our table of derivatives, right, we notice that the value of the second derivative, the function that we had, the value of the second derivative is 11, right? 11 is the value of the second derivative. So this second term can be rewritten as the second derivative of p at x equal to 0 times x squared over 2 factorial, right? So it's pretty convenient, right? So then if we go to our third term, right, we have x cubed and we have a 3 on the bottom. So what's this 13? Well, if we go back into our table, we see that 13 is the value of the third derivative of p at x equal to 0. So that would be the third derivative times x cubed over 3 factorial. Right, we have x to the 4th and we have the 4 factorial, and 17 is the value of the fourth derivative of p at x equal to 0, right? Plus p, the fourth derivative of 0 times x to the 4th over 4 factorial. All right, well, that looks like a pretty considerable pattern, but what about these first two terms over here? Well, right, so I wrote 1 factorial on the bottom for a reason, right? So technically, this is x raised to the first power, and that's over 1 factorial, right? And 7 is the value of the first derivative of p at x equal to 0, right? So this would be p prime of 0 times x to the first over 1 factorial. And 5 was the value of p of 0, right? And technically 5 is being multiplied by x to the 0th power, right? Because something to the 0th power would be 1. And we're dividing it by 0 factorial, and 0 factorial is just 1 as it is, right? So this would be p of 0 times x to the 0 divided by 0 factorial, right? So we're adding these terms up together, right? And presumably, right, if we had more, and we've established this before, if we keep adding on terms of greater powers, essentially we're going to be getting better approximations of the function, right? So we're adding these terms up together, and it'll go, and if we go on towards infinity, right, we get a better, and um, if it's infinity, then we get an exact approximation of the function value, right? So this is how this concept of approximating function values, this is how it ties in to series, to infinite series, right? So as you can see, right, we have this pattern, right? We have the second derivative times, oh, well, in this case, right, we have the second derivative times x squared over 2 factorial, and then we have, the first derivative times x to the first over 1 factorial. So this is a specific type of series. This is called the Taylor series, right? And the general form of Taylor series is, well, we're going to have our sigma notation over here, right? Let's start at, well, I'm going to say n is equal to 0, and we're going to go on towards infinity, because this is an infinite series, right? And each term in my Taylor series, right, it's going to be, well, let's use p's, right? It would be p, the nth derivative of p at some point a, right? A is the point that we're centering the series around, right? So in this case, in our case, in this case over here, a would have been 0 because we're centering the series at x equal to 0, right? So it'd be the nth derivative of p at a, right, times x minus a to the n, and a once again is going to be where it's centered around, and in this case, right, well, a was equal to 0, so we just had x to the n power over n factorial, right? So this is the general term of a Taylor series, right? And when the series is centered around 0, right, we have a specific name for it. So this is a general term of a Taylor series. So when it's centered around x is equal to 0, when it's centered around a is equal to 0, and the series looks like this, right, we don't have the a. This is called a Maclaurin series. And both Taylor and Maclaurin were mathematicians. So if you wanted to approximate the value of some function at some point, using polynomials, you would use this. You would use the general term of the Taylor series. And if you wanted to approximate the function value at x is equal to 0 of some function using polynomials, you would use the general term of the Maclaurin series. And the Maclaurin series is very simply just a type of Taylor series, just a Taylor series at x equal to 0, just like what we dealt with over here. So on the AP exam and on tests and stuff, you're going to be asked to construct a Taylor series polynomial, right? But obviously you can't go on towards infinity, right? So they might ask you to construct a third degree Taylor series polynomial at maybe x is equal to 2 or something like that, right? And in this case, you would go to the third degree, and you would take whatever function that they've given you, and you would find each derivative until the third derivative, right? And then you would multiply it by x minus 2, right? Because the Taylor series is centered at x equal to 2, so it would be x minus 2 to the nth power, right? Whatever term you're on, to the nth power, divided by n factorial, right? And that would go on until 3, because this is the third degree, right? Okay. So as you guys continue on towards the later sections in this chapter, you're going to learn the Taylor series representations of very common functions, right? Like sine of x and cosine of x and inverse tangent of x and e to the x and ln of 1 plus x. So you can actually create Taylor series polynomials for all of these functions using what you know right now, using these general terms. But later on in the chapter and in later sections, um, you're going to be asked to manipulate the Taylor series of these functions a lot. So you're gonna be expected to memorize um, the Maclaurin series for all these functions. This Taylor series centered at x equal to 0. You can be expected to memorize all of them, so you can manipulate all these series easily. So yeah, so hopefully by now you can see how applicable series are, and how we can use them to approximate values of functions at different points.